Yeah, I'm going to close today by sort of trying to give a condensed overview of what some of the topics are we're working on in my group. What we really have to do is trying to tackle some of the issues with full wave inversion that are related to the fact that it's computationally very expensive, even if you have a large machine. And so if there's one take-home message of this talk is that you do not necessarily have to work with all the data, and you don't always have to work with full accuracy either. And with that, you can make things way cheaper and more manageable. But to arrive at that conclusion, you need to do some work, and hopefully, during the next 1.5 hours, I can convey to you what that is, or at least you will know where to find it. There are references throughout, and let's start. Okay, so this is work that's not by myself alone, I wish, but with my co-workers. Tristan van Leeuwen, he was a postdoc in my group, he's now a professor in the mathematics department at the Utrecht University in the Netherlands. And then we have Sasha Rapkin, who just accepted the job at the University of Washington in the applied mathematics department. And then we have Michael Friedlander, who used to be at UBC, is now at the university somewhere in California, but maybe he comes back, maybe he doesn't. And what I really was talking about is randomized batching. For those of you who know machine learning or Google, that sort of batching stuff is there. So I try to make connections with different areas of active research. Okay, so what's then the goal for today? Is to come up with a fast simulation and optimization framework. Where we go our ideas from theoretical computer science, in particular machine learning and stochastic optimization. These techniques are used to speed up full wave inversion. We also try to use these methods to limit I/O. I think if Derek does his job, then computations are no longer a bottleneck. I/O will be the bottleneck, so you have to think about that. I try to come up with a method that is agnostic to the underlying wave equation-based inversion framework. So whether you do time stepping or time harmonic or whatever, it should, as long as there are costs that are sort of still the phenomenal sources, you're fine. And I will try to come up with a sort of a computational framework for FWI that only spends your resources when they're needed. And that's sort of the key message. So what does it not do? Right? It does not address the ill conditioning of full wave inversion. That's for Wednesday and afterwards. It's not about compressor sensing, Mike. Although some of these randomized dimensionality techniques can be used in compressor sensing, and we have used them successfully, I will not talk about it. I'm happy to talk about it offline, but not now. A lot of it's still sort of work in progress in the sense that it needs to be really taken to 3D and scaled to larger scale problems. One of the reasons we couldn't do that because we didn't have the compute, but now we do. So that's this. Codes are not yet optimized. I will use, for convenience, the time harmonic Helmholtz formulation and not time stepping, but everything I say will also pertain to time stepping methods. So don't zoom out and think this is not relevant. All my statements are valid to 8 hertz or so. So otherwise, so that, well, but maybe that's high enough for FWI need. So there's lots of room for improvements, to say the least. Okay, so if you are interested in the papers, we have a website. I don't know, the circles, I randomly sampled myself with this guy. You will find under publications, you'll find all, if you type in FWI in this field, you will find all FWI talks, or talks and papers and everything. So everything is out there under www.slim.us.udc.ca. We have also something like a mind map that tells us what we do in the group and how things are related. So this is full wave inversion, but we do also we do compressor sensing. And there's codes with all these things, and some of these codes are available. And certainly what I will be talking today will be available on the cluster in Brazil. That's ADP code there. So that's this. So that's not publicly available, but for the partners of this project it is. So everything I will talk about today has a concrete software implementation. Okay, so let's maybe talk a little bit about two-wave inversion. I know that my predecessors today have talked about it extensively. I will talk a little bit more about it, but in equations. I think most of you are physicists, hopefully, or mathematicians, or some computer scientists. So there's going to be some math. That's just a condensed way of formulating what we're trying to do. I hope I didn't go overboard. Let me know if you lost, if I'm losing you. Don't let me know too early though. Okay, so this is, and you will find papers like this. I will make a PDF available, then all these things are actively, so then you can download these papers. And so you will see them coming. Okay, so what are we interested in full-wave inversion? We are basically trying to get 3D models, gridded models of the subsurface, and some of the parameters we are interested in, for instance, is the acoustic wave speed, but it could be something else. And realistic problem sizes are large, about 1 billion unknowns, and then the data points is more than that. It lives in 5 dimensions, the model is in 3. So we're talking large-scale problems. Okay. Another complicating factor is that we propagate quite a number of wavelengths. That puts any wave equation solver in difficulties, right? So, and that's why Garrett's work is very important, and I hope to also the work we do. Okay, so what we have here is a setting where there's a source sending waves into the Earth, and then we have a physics that describes how waves interact with the Earth, and then that generates data, and then we collect that, and we try from that to make the appearances of the subsurface, but in a quantitative mathematical way. Okay, so what are you doing when you do waveform inversion? You retrieve the medium parameters from partial measurements of the solution of the wave equation. So miraculously, the notation of agent is pretty close to mine. It never happens. It's quite nice. So we have a restriction operator, P, that selects the wave field at the receivers and is indexed by I, and I runs over the different source experiments. So you either have the receivers stay put or they can move, right? And U is the solution of the wave equation, QI is the source, M are the medium parameters we're interested in, say the slowness, which is 1 over the block of the square. Okay, and then so we're trying to basically make this wave field restricted to the receivers match the data. That's what we're going to try to do. Now we use for that physics. I didn't see a single wave equation today. What the heck is that? But we're dealing with wave equations, and we're going to be time harmonic, so it means we take out the time derivative by taking the Fourier transform. We work per temporal frequency. And we're also going to assume that the density is constant, so we get rid of that. And we discretize, and voila, we get A on U equals Q. It was for radium, A equals Q equals S. Sometimes you will see an S in my case too. Notations always conflict. I talk about 5 papers, it's difficult to get the right notation. So if you see S or Q, it means source. Hopefully. Okay, so we have this system of equations. Okay, now, what's the challenge is that people want these systems of equations to be more and more sophisticated by bringing in more physics. I talk now only today about acoustics. If you do elastic or something else, you go right through the roof. So this is from BG book, it's years old. I think it's still pretty much holds. So computational costs are a real issue. And so what can you do to reduce some of these computational costs? That's sort of essentially what we try to do. But we don't do it characters. Now, we do also, but it's not the only component. We also try to really think, how do we work with data? How can we touch the data as few times as possible? Because all these algorithms are iterative. They tend to touch the data a lot of times, but when you touch the data, you're basically doing I/O, and I/O is input-output, it's expensive. Okay. So, the challenges really are, if you use any wave equation-based inversion technique, is that your computational cost linearly increases the number of sources. And there are quite a lot of number of sources, and therefore the computational costs become very quickly very high. In addition, the cost, as we saw earlier today, if you double your grid size, then the time, or you go, the velocity gets half because you get elastic, you go up with a factor of 16. That was very conservative because shear waves can be way slower than a factor of 2. So you can go up to 1,000 times more expensive, and there is no machine on Earth that can do it. So we have really problems if you want to do all the physics. There's no machine fast enough. And I don't think we have Moore's law, but we can have that. Okay, so what the key idea here is that we're going to introduce a fast randomization optimization technique that basically limits the number of times you touch the data. When I say a pass through the data, I mean that you touch all your source experiments, say once. That's a cost. And again, that cost determines how many wave equations you have to solve. So if you were to use all your shots, and you insist for each iteration to use all your shots, then you're going to spend quite a lot of passes through the data and therefore computational resources. Whereas if you choose to work with sort of subsets in a clever way, then you can get away with much less passes through the data and still get an answer that's very close. And if there's one outcome of our work, is that we've been able to convince industry of doing that, and people do this. Mike was also doing it, so lots of people were doing it ad hocly. We provided a framework that actually people that deliver services in this area do this, and found a good theoretical justification why you can actually do this. And that's really what I'm going to walk you through to some extent. Okay, so you can get with way less resources, you can get similar results. So just to brag a bit that the industry is doing this, so this is people from Schlumberger, and they have a very fancy random coil sampling technique that's the latest in marine acquisition. And they collect data in these sort of weird coils, and this is the gradient. That's the main ingredient of full wave inversion. These gradients you need to update your model in a manipulative way. And you spend normally an enormous amount of computational resources to get something like this if you touch all your shots. Because you basically run a loop over shots, and you get lots of shots, you have a lot of work to do. Right? Whereas if you use randomized techniques that we've been proposing, the gradient is still very acceptable, but you do it at a fraction of the cost. And they have done this, and it has resulted in about 4 to 7 times increase, I don't know what happened here, increase in computational speed, making the difference between a loss or a profit when you deliver a service based on this technology. And that's something they really value. So you bring value by doing it. Alright, that sounds all fantastic and great, but you know, why would I believe this guy? Why can you do this? So I'm going to spend remaining, I don't know how long. Mike, you're going to keep track of my time. As you maybe start and you hear out of it. Okay, so where are we coming from? Just to basically say, what is this? Where does this crazy stuff for propagating and taking residue and correlate? Where the heck does that come from? It's sometimes good to know where things came from. So I think it's fair to say that what we really set out to solve is something like this. We don't, but we should if we have a computer. And what we're trying to do is to jointly, basically, or to minimize over all wave fields. So this index runs over the source experiment. But for each shot, you have one index. And let it also run over frequencies. Right? So it's just something that runs over monochromatic source experiments. And so the costs are here because you have to try to find a wave field that solves the wave equation but also fits the data. And so you're inverting both for the Earth model M and wave field U in this constrained formulation. That's a very nice formulation. Unfortunately, given the size of our problems, we cannot do this because you would have to store all of these, and that doesn't necessarily scale to industry scale problems. So what people do is that they basically eliminate this PDE constraint. Because what we're trying to do is find a wave field that matches the data such that it also solves the wave equation. Right? That's really what we do. So we get rid of it. And how we do that is by setting up a Lagrangian formulation so that it becomes worse now. Now we have unknowns and so we start first with submissive. I'm making it even worse. I'm introducing a wavelet here. So I'm going to estimate the wavelet in fly. So if you look at the general formulation, is we try to basically minimize some sort of misfit of the weighted data, weighted is a source function, and the wave field such that you solve a PDE. And then we form an ugly Lagrangian, where you have the Earth model as an unknown, the wavelet, the forward wave field, and the adjoint wave field. And that's equal to this. And then you can eliminate basically both the wavelet and the state variables by solving the wave equation and by solving the adjoint wave equation where you insert the residual by computing this for the wavelet update and by doing this for the model update. So this is the most difficult, most massive slide. Won't get easier, but it's sort of good to know where did these methods come from. Okay, so in the end, if you do all of this, you end up with a formulation where you have to solve a forward wave equation. Adrian already talked about that. Where given the source, you want to solve for the wave field. Then you have a data residual, which you inject, and you have to solve the adjoint wave equation. And then we find the wavelet by solving this minimization problem. So that's all nice, and that in the end gives you a formulation that has a particular structure that we will be exploring. And the particular structure we have is that we're going to try to minimize a misfit function, which consists of a sum over different source experiments of individual objective functions, which are given by this, which is basically the misfit between the data that you generate with your forward modeling and the observed data. And so we need to be able to compute this objective that measures how well we are explaining the data, and we need to be able to take a gradient with respect to the model parameters, which is given by the gradient of the model parameters for each individual objective, and that is given by the cross correlation between the forward wave field and the adjoint wave field multiplied on omega squared. So Adrian showed it. So what it basically tells you, you have to solve a heck of a lot of forward and adjoint wave equations for each I, and I runs over the number of experiments, and that can go in the large numbers. So that's basically the challenge. Okay. So if you put it now all together, what we are solving is a reduced misfit functional where we really solve the equation. We eliminated the constraint, so we're solving this problem, which is nice. We don't have to store the wave fields, and we can use sort of black box optimizations, and we're going to concentrate on this one and using random sampling techniques to basically approximate this sum. That's what we're going to talk about. We're not talking about anything in red. That's for Wednesday, and yeah, that's for Wednesday. Okay, so for that we came up with something that we call frugal FWI. Frugal FWI meaning in Dutch, we're stingy. So in this case, we're stingy in the amount of computations we want to spend. And so this is the framework, and we published that in a bunch of papers. There's a sort of an informal paper in Leading Edge, and then we just got this accepted in CISC, which is a scientific computing journal from science. So everything that's discussed in the paper will be in the talk, and some papers that are predecessing it. So it's sort of a heroic effort for me to combine all these different results into sort of one framework. Okay, so what's the challenge? Just to make sure that you really understand, is that computational costs scale with the number of sources. So what we're going to do is to reduce these costs by working with subsets of sources. Okay? Yeah, sure, you can say that, but does that really make sense? Can you make sure that things still converge? Can you convince management that this is not such a bad idea to do? Okay, because they spend a lot of money collecting data, and they have ingrained in their cycle that all the data has to be used, because the more data you use, the better. Actually, that's not necessarily true. So, it's easy to pose the strategy, it's not so easy to solve. Another thing that people may hate is that we're going to allow for inactive physics. So we're not going to exactly eliminate the constraint. That's a dangerous game. Because when you eliminate constraints, you typically have to eliminate them exactly. So that's a very dangerous game. I'm going to try to come up with techniques that prove that you can have convergence guarantees and that we can sort of dial in the accuracy as we go, which leads to some algorithm that basically select automatically how many shots to use and how accurately it needs to solve the use. That's the key idea. And both are basically determining how much compute you need. That's the key idea. So the outcome then is sort of affordable between posts and the right. This doesn't mean that you don't need a big cluster. It just means you can do bigger problems on this cluster. So there's a lot that goes into this, and I hope my time permitting, let me just look at this, up to 20 minutes, so I have 5 more time. 6 times, so I may have to slow down. So we need a lot of different components. Now you can argue about whether these are the best choices, and the way we think about this is that we do it in such a way that we can swap in one component yet or not. So when you see Helmholtz, you can say also, I'm going to do time solving. Right? So there are things, it's very modular in that sense. Now we choose a Helmholtz solver. Now, solving Helmholtz equations is one of the biggest problems in computational linear algebra. And occasional people come up with fantastic preconditioners, and they're great. But they are not so great because they need enormous setup costs. And if you have large setup costs, you can do that if you want to simulate once. You cannot do it when you do an optimization procedure where you continuously update the model. Because if you update the model, you have to incur the same costs again. That's a problem also with finite elements. If your meshing is very expensive. So we want to control those costs. So that's the computational overhead related to setup costs. Also, we don't have necessarily a lot of memory. Our models are very large. Keeping lots of copies of the data is something we cannot necessarily do. So that already constrains enormously what you can do given existing techniques. Another thing that you often see is that these preconditioners need tuning. So they work for one model, but then they may not work for another model. Well, good luck if you run an optimization procedure where your model changes all the time. How can you make sure that things actually work? So we want something that is also stable in a way. It doesn't need any tuning. So that's for the solvers. And I will talk a little bit about the solvers. Then we need a practical stopping criterion. Namely, we don't want to solve these wave equations where we use iterative methods to solve them accurately if we don't need to. Right? So we're going to only dial in accuracy when it matters. Right? So that means you want a formulation that you can do that. So if you do an iterative solver for Helmholtz, if you limit the number of iterations, then you could typically do that by just stopping. If the error behaves sort of not. To speed up things, we're going to use techniques from stochastic optimization. I'll talk more about it later. And we want to be able to, of course, exploit parallelism both along the data. So, for instance, the parallelization that's very natural is over shots, say over experiments. But you can also do things like domain decompositions or other tricks that parallelize the PE solver itself. So the 2 levels of parallelism. Okay, so we're going to go through all these topics, and I'm not sure I will cover all of them. I may run out of steam, or more likely you guys will run out of steam. But I will touch on all of them, and unfortunately, you'll need all of them, right? So you need a framework that allows you to solve the wave equation in a very efficient way in the context of the wave equation. Right? So it's one thing to solve a wave equation, it's another to solve it in the context of solving a full wave equation. These are not necessarily the same. Right? So we design solvers that are very good when you solve optimization problems, like FWI. They may not be good if you are only interested in simulating waves. It's a different question. Okay, then we can think about how to come up with a formulation that's maybe robust with respect to outliers. So noise is often assumed to be white, but it can be something that's not white, so you can use different than energy or L2 misfit function, so that's sort of in this row. That's at the end of my talk, if I make it. If not, you can come and see me and I will talk about it. And then there are fast optimization strategies. A lot of time I will spend here, because they are the stochastic optimization techniques that allow us to work with small subsets of data and as such make much faster progress to the solution than if you were to work with all the data all the time. If you want to remember one thing out of my talk, that's the one. Right, so you can zoom in now and then now. Okay, so let's talk about this versatile modeling. Okay, so that's challenging, I tell you, and it's a big headache. And might maybe for good reason move to time-stepping methods. We are doing that also, but they are also a nightmare. So you have two types of headaches, right? Time harmonic or the time-stepping. They're both headaches. So it's not so easy to solve these things. But for now, I will stick to doing things with time harmonic. Now, why is it troublesome? Well, because we have a lot of grid points. I will not scale to this side of the problem, but even on tiny little problems, you can see that these computational costs become insane. By the way, everything we show, nothing is optimized, it's all single-threaded. So if you see numbers and you're upset, you should be upset because we didn't optimize. Right? So don't disregard anything I say if you look at our numbers. They can get much better if you put in the time. Now, what's the challenge that really with these time harmonic things is it's a matrix, it's a system of equations, and it is, if you look at the eigenvalues, it's indefinite, it has positive and negative eigenvalues, which makes any iterative Krylov method scream to a halt. You can't handle it. So you need to precondition the system. And you need to do that when you go, in particular when you go to high frequencies, when the system becomes increasingly indefinite. This is a nightmare for linear algebra people. That's why either they walk away from this and go to parabolic, diffusion problems. Waves, a lot of scientific computing people walk away from because it's so difficult. But you see now that there's more and more people starting to work on it. I was at the ECM meeting, which is the overarching math, applied math meeting in the world in Beijing 2 weeks ago. And Björn Enquist, who's a big scientific computing guy, gave a talk on FWI. So they are trying to do it because they're faster computers and because it's a cool topic. We yell enough to get their interest. Okay, so the strategy then is to come up with a preconditioner that avoids large startup and memory and tuning parameters, and this is going to be important. Sometimes there's some repetition, but make sure that people. I didn't like. Originally I had learning balls. You know what it is? Who's the professor here? So we as professors are forced to write learning balls for our students, and it means that you have to agree before you give a lecture what they're going to learn. So it's basically a good check though, because you can basically have a checklist that students actually learn what you want them to learn. And it's a checklist for both the professors as well as the students. Maybe next time. Okay. So we're going to play basically with a number of iterations, and that can dial in position or not. And so the outcome of this is a scalable parallel wave equation solver that can solve wave equations up to a prescribed tolerance. And it's a very simple preconditioner that works irrespective of the wave distance. So a lot of work has been done on preconditioners where people optimize the heck out of a 7-point stencil, or 9-point, whatever stencil, and then somebody else comes along, I want to add it on a 27-point stencil, and then I have to rewrite the preconditioner. Or you should have a domain-specific language for preconditioning, or something like that. So this method doesn't suffer from that. Or if you go from acoustic to elastic. Right, so these things are important, and it's also important that this remains to work. So what we want is something that may not be a Ferrari. It's good enough to get it around the circle. Okay, so what's this Seismology method based on? And people that know about preconditioning do laugh, because people that do only preconditioning for a living and solve almost equations say, what the heck, this is 20-year-old technology. But these guys do not think about that you actually have to solve an NWI problem, right? So it may not be the newest and the latest, but it is something that serves our bill, and that's different than just solving wave equations. Okay, so what we do is we do this sort of very simple row-by-row projection. So AI is the ith row of the Helmholtz matrix, and you iterate this, and then there's some relaxation parameter here that you can choose. There's 1, 2 tuning parameter that's quite mundane. That can in principle solve an AX equals B system. It's like the 101 in inverting a matrix. It's consistent, it will solve the inverse of that matrix. Okay, that goes back to Seismology, back in 37. So it's these projections on the different constraints, and this is what happens when you play around with the line. So we're going to use that to come up with a preconditioner for a conjugate gradient. So we're going to rewrite it slightly, that you have this system here, I minus QI, so I here refers not to the shot, but it refers in our sort of notation, it refers to the ith row of the Helmholtz equation. I'm not talking about solving Helmholtz equation. Get shots. Okay, and so you can do that for each row, and then you can basically write a double sweep. So it's in a way you go down to the matrix, row by row, do all these projections, and then you go at the bottom, and then you go back up in reverse order. And that's a double sweep. That can be written as a product of all these matrices, and this matrix is symmetric. As long as you do the same thing going down as going back up. And then you also define this R which collects all these terms. So we're doing some linear algebra. So what happens now, you can form this system, I minus Q on X equals RB. This you can solve because this equation here is positive definite. Means you remove the definiteness, now you can run any iterative solver. And conjugate gradient is the one that we use. And that's nice because conjugate gradient is a nice iterative method that knows how to invert matrices as long as they're positive definite. And this is all shit. Sorry to use the word. This goes back to these guys. There's nothing sophisticated here, but it fits our bill, I think. Okay, so I think I'm going to check this is redundant, so I'll let that go. So what is sort of interesting is that you can see that this is basically equivalent to some relaxation method. SSOR, I forgot what it stands for, you may know that. You know about preconditioners. But you basically do preconditioning of the normal equations. You can identify this Q and R in terms of basically that you do a preconditioner that sits between H and SPOs and A. And this preconditioner makes the system positive definite. Thanks. And these sweeps, what do? They go from I equals 1 to the number of rows in the matrix, they do this, and then they go backwards and they do that. It's a simple algorithm, we even implemented this on FPGAs. That was a nightmare. But any of these low-level languages are a nightmare, frankly. But it's not that far from time stepping. So maybe you can do something with time stepping and on-the-fly stencil generation, you may be able to do something. Okay, so this is the big DKSWP, the double sweep. But that is equivalent to doing these operations. And these operations were essential to form the CG. So you can basically call CG with this function double sweep. And you basically accelerate the Seismology with conjugate gradient. So I'm not going to talk too much about it, but I will touch a little bit on some recent extensions where we speed up the heck out of this thing. But for now, just to say a couple of things. First of all, this is in principle matrix free, has very low setup cost. As I said, it can be applied to different physics. Jean Bourdieu has applied this method on elastic applied and using the same code that we would use for an acoustic applied. So I have the preconditioning method. That's something, so there's a proof of principle right there. We have a proof of principle that it works for different discretizations. So if you go switch from one discretization for a Laplacian to another discretization, the thing still works, which is nice because lots of preconditions will be broken if you go from one to another discretization. Sorry, I'm very technical here, but I do that on purpose because this sort of technical detail goes into, unfortunately, into SRI. It's one of those new components that we have, and this is one of them. Okay, so I think it can do on-the-fly generation extensions. We don't do that yet. If you give us that sort of stuff, we will do it. Okay. It can also be extended to work with multiple sources, multiple writing sites. Instead of CG, you can work with CR, which is another type of solver that is maybe converges a little bit faster. And it can be combined with multi-level techniques, which are multi-grid techniques. So this is a little bit linear algebra lingo, but these are just techniques to speed up or precondition these systems so they can actually solve them. So just to run you through a couple of examples, again, none of these are optimized. Some of these are humongously slow, but that's because nothing is done in multi-threading or anything. But it tells you already how difficult it is to solve these problems. Because it gets very quickly and very expensive. Okay, so you have an overthrust model. We have 27-point stencil with about 10 points per wavelength. And it's sort of the physical dimensions are of this size. And this is the hardware we use to do some of these things. Okay, so here we compare this method to some other methods people have come up with. And so for instance, you could be naive and use big stack or GMRES. And of course, ours is CGMN. And this calculates the number of iterations that you need to do. And this is the residual. What you want is that the residual goes down fast. That's the key idea what you'd like to have. And you can see that for very low frequency, so this is for only half a hertz, completely, utterly irrelevant for a full wave inversion, because that typically starts at 3. But it tells you that the number of the complexity of these things goes out of the window very fast if you go up to, in frequency. So if we go to 1 or 2 hertz, so this is 0.51, this is 2, and this is 4 hertz, you can see that the black guy no longer converges. Doesn't work. Can't deal with it. Boom, out. And the decay of the blue one is very slow, whereas this guy still makes progress, but needs quite a number of iterations versus if you were to do things at a lower frequency. Now, it's the increased indefiniteness, the fact that you typically have to have a finer grid at higher frequencies, the fact that the system is less low post, all factor into the fact that you need more iterations as you go to higher frequencies. And here is a table saying the same thing. What you can see, what is really scary is the number of unknowns that increases with frequency. Because as you go to higher frequency, you need a finer grid. These things go through the roof unbelievably fast because the doubling of the grid size multiplied everything is 8. And then the times go up accordingly, which is not good. Right? So this tells you that we are dealing with a computationally challenging problem. CGMN is the only one that was able to do something at 4 hertz at a price. These were seconds. It's a long time to solve a relatively small problem. But again, this is not optimized. So I think you can get easy do multi-threading over right-hand sides, do all sorts of things to make these numbers more palatable, but still, they're not. So one thing you can do to speed up things, I'm not going to spend too much time on it, because I have an infinite time slot, but it's not really infinite, so I will sort of close down on this Helmut business. Is you can do things with block CG, where you basically use the fact that you have multiple right-hand sides. So sorry, now notation, now S is really the source, not Q. And S is uppercase. Uppercase typically means in my notation it's a matrix. And the matrix is made out of columns that are the different source experiments. Right? So you have now multiple right-hand sides, multiple sources, and you try to solve for multiple wave fields. And you can do that typically faster. So and forget the details of the algorithm. I had a bunch of algorithms, some will go in detail over and others won't. But these are really pseudocodes that you can use to implement this or understand the code we wrote. So that typically helps if you increase the block size, so things will decay faster. Well, that improvement goes out the window pretty quickly if you go to higher frequencies. Even though it helps, it doesn't necessarily help a lot. So our real challenge is to still solve this Helmholtz equation at high frequencies, so large-scale problems. Right? So that's nothing new. Time stepping from the large volume is also expensive and has its own challenges. So there you go. And there's a table here that says the same thing. Another way to speed up things is doing domain decomposition. So now the algorithm becomes called CarpCG, where this carp stands for you to do things parallel over blocks. And that thing sort of scales, but not fantastically, certainly for higher frequencies. Whenever it's not flat, it's not good. So then you're not really gaining. And if you look at what is this? So this is number of processors against number of iterations. So you want that to be flat, but it's not. And this is the time per iteration. And you want that to go down like this and not flatten out, but it flattens out. So it's not perfect, but it does something. We're not yet clear whether we want to use this or we want to use more parallelism over the right-hand side. But it gives you an idea that you can do these things. And this is all in code, that part of it is available. Now you can change CG with CRMN. Let's not spend too much time on it, but you can game with that. So this is time in minutes, that's way too long, but it's for the overthrust model with 8 curves. That's sort of the largest model we can handle at the highest frequency. You still see that takes 400 minutes, that's too much. But again, this is not super optimal. So we do a little bit state of the art, but this is now 2 minutes for people that are hardcore Helmholtz solvers. We have really built a 3-bit multi-grid precondition combined with everything, and that's work we did with Igor. He's in the back, he was a summer student. We worked with Rafael, who used to be in my group. And our method beats the fastest solver that was developed by Total, by Henri Calandra and those guys. And we changed this very fancy guy where you see all these Genresses and Jacobi smoothers. We changed them by just doing part switch. We can do that for any stencil. And correct me if I'm wrong, but you look, I'm saying something back, I don't think so. So we can change all these boxes here with CRNs, and that makes the thing much less sensitive to the discretization and all sorts of things. And it's faster. I believe these guys. So there's a plot here that's in red and in black. That's sort of what we do, and it wins all the time. Where we go here, this is for that's for 7 on the left, and on the right for 27 points. So other methods are dependent on the grid. So if you just put a 27-point grid in there, they hopelessly fail because they weren't tuned. Right? All these Fourier analysis they have to do to tune it. You can't easily do that in a DOM method doesn't do that. So it basically shows that you have something that is sort of works for different types of systems. I'm going to just skip this. So, and end my little digression on how to solve large-scale systems, right? So, I think we have with this Schwarzschild a preconditioner that is independent of the underlying physics and of the discretization, which is really nice, because you can optimize something that can do row projections row by row, and if somebody like Derek can come up with a blazingly fast software implementation that does that with on-the-fly stencil generation, then we have a framework that could basically deal with lots of different physics, as long as you have the stencil. What I didn't talk so much about is produces smooth errors as a function of iteration. So if you increase the number of iterations, the signal goes down smoothly. That means that you can, when you stop, you basically have a sort of tolerance and it behaves nicely. It doesn't jagger around. And it can handle multiple writing size and does scale to 3D. So that's it. Okay, so that was one little component. Maybe while I take a sip of water, people can shoot questions or switch completely context and go to another. Maybe not. It was a bit technical. Yes?
One other idea is to impose constraints over the model. The model would obey to some sufficient distribution.
Well, I think in this case we would like to do that on the solution. Maybe difficult to get that fast. Mind you, so far I only talked about solving wave equations, simulations, not solving FWI. Wednesday I will talk exactly about what you're talking about, to constrain the model. Yeah, there was a question here.
How about the size of the segment?
You mean the fineness of the discretization?
If you have a lot of shots, then you have shots.
So, well, typically the different shots are sampled in the geophysical setting that we mostly care about at the surface on a two-dimensional plane. And then depending on how much money you have more or less shots. And so, and then the unknowns is the wave field everywhere. But the sources are only living at the surface. Okay, so I can easily talk a whole lecture only on solving wave equations, but unfortunately that's not what we need to do. We need to also come up with a optimization framework that allows us to turn these simulations, given data, into model updates, right? Into an optimization scheme that produces something reasonable. Now again, I'm not talking about all sort of ill-conditioning problems and cycle skipping. That's for Wednesday. I will only talk about the mechanics and how to make this work. So for that, one key ingredient is that we use dimensionality reduction ideas. Some of that is related to compressive sensing, but some of it is related to what Google does. Google gets enormously large data volumes, and they don't have to compute to look at all the data points, but they look at random subsets. And then do that through a dimensionality reduction technique. And there are a bunch of papers that deal with that. And I'm going to try to summarize that for you. Okay, so we're going to really leverage that there is very particular structure in full wave inversion that we can use. And there are two key components to the structure that we have. One we already talked about. That is, there is this separable structure. The objective that we try to minimize, that basically expresses the misfit between observed data and the syntactic data that depends on the Earth model that we're trying to invert for, that has a sum structure because you sum of all source experiments. Right? And this sum is like an average, and you can approximate averages by sampling. So you use basically statistical techniques to approximate that sum. Another thing is that the misfit function has this residual, and this f is basically the wave equation inverted, and then you apply the restriction operator that brings you to the receivers. That's linear in the source. So the physics is linear in the source. It means you can look at the response of one source, or you can randomly combine different sources, and they give a response, but that's the same as the response of all the individual sources, and then combine them after you apply the solution of the waveform. So you can do, basically, you can use superposition principle. So, how can we then reduce the cost? Well, you want to limit the number of terms in this sum. So one way of doing that is saying, you know what? I'm only going to compute that sum not over all n elements, but over a random subset that is smaller than that. And I have computational gains that way. And you can do that by just randomly selecting sources, and that would work for any PI. So I index here P is I, that means that different sources can see different receivers, like in the array. If you show an array, then you move the sources, but you also move the array with you. So different sources see different receivers, and that may break some of the tricks we can play. Another thing we can use is source encoding. And there we form source aggregates using linearity of the problem with respect to the source. And that only works when we have a fixed, the receivers are fixed, so all the sources see the same receiver. So think an ocean bottom cable and some guy in a speedboat having the source going, the source behind him and firing. Okay? And that does not work for any other than listed functionals than the L2. If you want to do something else in L2, then come to talk to me. There's some reason for it, but in principle, these source aggregates don't work. So let's first talk a little bit about this sort of batching or selecting subsets of shots. Okay. So what we're going to do is nothing very fancy, but if you get into the details of it, it gets a little bit mucky because you're doing this optimization problem and, you know, things have to converge and da. So but let's just look at this, what happens, right? So we can go approximate this misfit function by a misfit function tilde, which is taking a random subset of the shots. So you basically tell your code not to loop over all the shots, but over a random subset. And that subset is smaller than the total number of shots. So in math, we basically choose indices amongst all possible shots, and then we want the cardinality, that is the number of elements in that set, to be smaller, much smaller than n, which would be all the shots. So we do less work. Great, right? So, well, that's nice. But you need to be careful, right? You create errors. This is not equal. These errors will decay as k gets bigger, but you need to prove them. So if you take more, you have a randomized algorithm, you need to prove that in expectation, in the end, you get the right objective. So that's what we wrote here. If you sample these guys uniformly, you can take the expectation over how you select these guys. If you take them uniformly, in expectation, the psi, phi, I always forget, and tilde, objective, tilde, approximated objective converges to the two objectives. Well, that's nice, because then you have some guarantee that in expectation things work out. So do the gradients. So if you work with random subsets in expectation, you will get the true problem. And so if you are smart, you can approximate this with a small sum, you may gain something. Okay. So now you can ask yourself a question, right? And this is actually still open for debate. In the context that I'll talk about today, what I will say will make sense, but in compressive sensing sense, it may not. So, but let me say, right? If you have a choice to select shots, you select for one gradient of data subset, and then the next one, would you like to choose another set, or would you like to maybe select still something you had in the previous? That's called with or without replacement. So if you do it with replacement, you selected the shots and you put them back in, so you could select them again the next time. Without replacement, you took them, and now the set becomes small. And in the end, you will touch all the data if you did enough iterations. Okay, so that's without or with replacement. Okay, and then you can write down something about how the variance of the sample averages, so how the sample averages, what the variance of that is, because that's a statistical parameter now that has variance, right? how that behaves as k increases. And then you will find that both these techniques, with or without inflation, will depend on the sample variance that expresses the difference of each gradient with respect to the gradient, the full gradient, as if you used all the data, which you never can, but theoretically you can talk about it. And then you can see that if you do it without replacement, the error that you make scales like this. It means if k goes to m, the error goes to 0. Whereas if you do not, if you replace, then the error will go down very, very slowly. It will never really go to 0. Right? So, and there's some theorems on building this, but this is sort of it's important because it tells you, should I basically select the things, or should I basically always make sure that I touch all the data, or can I just always select among the same number of shots? And it's clear that you should do things without replacement. It means you select them once, and then you don't select them at later point until you touch everything, and then you start over. Okay, so we can look a little bit at how does the error behave as a function of k, and again, k is the number of shots that partake in computing the objective or the gradient. Right, the smaller k is, the cheaper things get. Okay, and then we can look at the worst case, which you can write down mathematically, forget it, but it sort of depends on what's the worst error you have, to random without replacement in red, or random with replacement, which is really similar to doing randomized source encoding, which I will talk about in a minute. So theoretically, you have these curves, so there are very big differences between them. So if you do random without displacement, this thing really will go to 0. If you do it with replacement, you will never go to 0. You decay very slow, but in the beginning you decay fast. But then at one point you saturate. The worst case in the end will go to 0, but can be really bad. It never happens, but you always want to hedge for the worst case. So that's on the left. On the right are some random simulations, and you see some error bars because you're talking about expectations. Basically, it's an expectation of the error, and so when you do things simulation-wise, you will have error bars. But it sort of corresponds with the trend that the theory predicts. So the theory predicts that if you select randomly without replacement, you bring your error down as the number of shots in your batch as the sample size increases. And you just do that by randomly selecting, but you don't put them back in the shot portfolio. Okay, so that's one way. Another way of doing things is to do random source encoding. That was a technique invented by migration people, and then Total did something, and then ExxonMobil made a huge splash with this doing source encoding. So what do? They basically use the fact that if you have all the received, you see the same shots, you can randomly combine shots into so-called super shots. Right? That only holds where your forward knowing operator has the same key and you have a 2 non-listing. So then you can basically randomly combine sources. So what this means is that we give every source a random weight and sum them. So you have an impulse of source somewhere, give it a random weight, with an impulse of source somewhere else, give it a random weight, do that for every source location, sum, boom, into one crazy super shot. Okay? So you can think of your source matrix as a source is a matrix, that every column is a different source experiment, and what you do, you hit it from the right with a random vector with Gaussian noise. And that turns a sequential individual shot into a shot where all shot positions fire with random waves. So you send a crazy incoherent wave into yours. You can do that because you're linear in the source. Now what's cool about that is that actually will allow you to do the same thing on the data, and you can work with way fewer shots this way. You subsample shots because you have few of these simultaneous sources. And again, if you do things right, if you choose these weights in such a way that their covariance is some scaled version of the identity, then you can prove that in expectation you will go to the true objective. And we still see this is the data filter, which is basically the data organized like a matrix, and then into W. So you can do this. It's called sometimes simultaneous sourcing, because all the sources fire at the same time. Okay, so let's look how things behave if you do that. And let's look at the Silex example, where we play with the number of these simultaneous sources. And let's look at what sort of errors we create, because sometimes the image is way better than a bunch of equations. Okay, so we have here a true mean model. So this is the true velocity in color encoded. This is the starting model, good starting model. And this is the perturbation. This is what we want to recover, giving this as a starting model. Okay. So let's first look at some gradients, what they do. So this is the search direction when we either are fully sampled, when we have only one simultaneous source going off, where all the sources have random weights, so you get all this source crosstalk, because all these sources are basically talking to each other. And as you increase the number of simultaneous shots, that sort of noise will cancel. It cancels very slowly. This is like a Monte Carlo sample, in a way. And so this is the gradient. So we have some notation here. I don't know why I have the slide here, but I think something is flipped. But this is the data residual. This is the basically the adjoint of the Jacobian. So this whole thing gives you an individual gradient. And then you sum over k of them. You do that for k simultaneous sources. And you do this also for data that you make simultaneous by doing the same random weighting on the data set. In this case, much smaller than that. In this case, only one. So this is 1 PDE solved, this is 10 PDE solved, and this one is OM PDE solved. Right? Because things scale with the number of sources, because the number of sources basically describes how many PDEs you have to solve, and that's the cost. This is what I should have shown earlier. This is objective. So I just showed the gradient. This is the objective. So this is a number that we try to minimize, where this is the and we do this in the direction of the gradient. That's why I showed the gradient first. So what you want is that these coincide with the true. I think the true one is in red, and then these different color ones are different randomizations for only one simultaneous source, 5 simultaneous sources, and 10 simultaneous sources. You can see that for 10, the minimum of this objective is sort of the same for all. So instead of doing a loop over 100 shots, you can do a loop over 10 shots, you get pretty close. That's the basic message. Unfortunately, the error of this deals with the square root of k. So the error doesn't go down very fast, which is intrinsically in any Monte Carlo practice. So this is the decay of the error, that goes pretty slow as a function of k. Now, when you use these simultaneous sources, there's a link with a research direction that's called random trace estimation, because what we're really trying to do is estimate the trace of RTR, and R is the matrix that has the residues for each shot in the columns, and this is sort of the data misfit that you try to minimize. And you can approximate this trace by basically probing it with these random W's. That's exactly what we've been doing here. Here you see the full wave inversion problem where Q are all the multiple sources, D is the data for all the different sources, and W is a vector for a matrix that you hit on the right that turns all these experiments into simultaneous source experiments, where W is skinny, so it has few columns, therefore few PDE solves. Okay, so what we have a way to stochastically sample objectives and gradients. Now we still have to turn this into an objective framework, an optimization framework. So we can use stochastic optimization for that. So we can do two things here. You can either use stochastic average approximation, where you really use the fact that if you do these random sources, you introduce a randomness, if you take an expectation with it, you have the true objective. You can do that in this way where you approximate the expectation by a sum. So that's one thing you can do. You can basically say in words, you say, I'm going to select a subset of random shots and I'm going to work with those. And then fix it. Right? That's one thing you can do. Another thing you can do is you can do the stochastic approximation. So what you do there is, you say, I'm going to select a random subset of shots, and every gradient step, I'm selecting a different set. You select a set, compute a gradient, and in the next iteration, select another set. Right? That's called the stochastic approximation. That's what the Googles do. That's how stochastic optimization that drives all these machine learning techniques. And you do exactly that. Okay? Now that can converge under certain technical conditions, but it's sublinear. So if you have an optimization method that normally has a linear convergence, now you're sublinear. That's bad news. But the convergence is very slow. And you can sort of understand that because every time you select a different random subset of sources, you're slightly going in a different direction. So you never go to the minimum, you always start to circle around it. That's the disadvantage. So, and it is sensitive to noise. So here we have an example where we work with one super shot. So we convert all the 100 shots into one super shot and have a different super shot for each iteration. And then if you don't do things without redrawing or with redrawing, without redrawing you get this, with redrawing you get that. It's very good, it's noise free. But if it's noisy, then you diverge. So you have to be very careful when you use this method, and I'm going to skip all the technical details. But that's sort of what the field of stochastic optimization is. But that's unfortunately not good enough for what we want, because we want guarantees. So that really brings me to a hybrid method that tries to do both. It tries, on the one hand, to reap the benefits of the stochastic optimization technique, because we can make very fast progress with the solution. On the other hand, we want to guarantee that we get the solution that you would have if you had infinite computational resources. And for that, I will be a bit technical and then I will wrap it up. So let's look at the simplest of the simplest of the simplest optimization schemes. Right? So we have a model at the current iteration k that we update to k plus 1 iteration through the search direction that's defined in terms of the grades. Okay, so this has linear conversion rates. That means if you know your conversion rate, it scales with some unknown constant to the power k. That constant depends on the conditioning of your system. Okay? So what we're going to allow now is an error. And we have an error because we are using these random subsets of shots that introduces an error. So we have an error in each gradient. Now we can still make sure that the difference between the objective at the k iteration and the objective at the true solution to k is like this. If we choose this is what it is, but if you choose the e's smaller than the ck's, we are guaranteed to make the same progress as the original algorithm. In other words, if we control the error commensurate the convergence rate, we're fine. That's basically the key idea. So you have to control the error. How can you control the error? By increasing the number of shots that you use in a calculator. So you control the error in a way that's commensurate with the conversion rate of your algorithm. So then you can get basically the best of both worlds. So you have here, this is linear conversion. So in green is the, let me see. So the one that I'm talking about is the red one. So the one when you don't do this increase of your bed size will basically saturate, will never get to 0, but this one will. So a couple of general statements because there's a lot of misconceptions. A lot of people think if I have a really ill-conditioned system, I should use as much data as I have. What I'm going to tell you now, that is absolutely not what you should be doing. Okay, so what I'm going to say basically is this. If you want to design an optimization scheme with a linear conversion rate, which is sort of the optimal way for the first order method, then you need to grow the batch size in such a way that the expectation of the error decreases with at least that rate. That's one. Secondly, there's no benefit to increase the batch size, that is the number of shots that you use, at a rate faster than the rate of the original problem, namely that c to the power k. In other words, when you have an ill-conditioned problem, where you have a Liacir constant that ties the gradients to this guy, if that's small, when the problem is ill-conditioned, don't work with a lot of data, work with little data. That's not, I don't think anybody in the room would have guessed it. That's what you actually, this sort of analysis gives you. Now that gives you the same kind of problem, because we don't know what the conversion rate is. Great, that's where the mathematicians stop. And now the practitioner has to come in. How the heck are we solving this? Do we have still 15 minutes? Yes. Okay. Because then I will come up with a practical algorithm that does this, and then everybody deserving the practitioner to deal with it. Okay. So, okay, so that brings me to basically combining these things. Okay, so let me just skip this. So we're going to come up with an heuristic. It's awfully difficult to prove anything. But I'm coming up with an algorithm that we have coded in MATLAB, and it does what it's supposed to do. Namely, dynamically choosing how many shots should I use, how accurate should I solve the wave equation. So, okay, so what is it going to do? It's going to look at the behavior of the misfit function as a function of epsilon. So we're going to introduce basically something where we allow for an error in the wave field. We're going to basically say we're going to solve the wave equation up to tolerance epsilon. Not 10 to the power minus 6, no, 10 to the power minus 1, something bigger. Okay? So we solve the PDEs up to tolerance epsilon. Now, ideally, we would like to find an epsilon that guarantees that we control the error in the objective. So this is the objective when we make no error. This is the objective when we make an error, and we want that difference to be some fraction of the true objective. Unfortunately, we never know what the true objective is. So, because we can't spend cycles to compute it. Right? So, for that we're going to use a trick. We're going to basically do an iterative algorithm where we introduce a k, and we loop over this, where we dial in basically the epsilons until until this equality holds. So that allows us to dial in accuracy only to the point that you need, and then stop if you're within some fraction of the true objective. Now this is a heuristic, very difficult to prove in the But that leads to an algorithm. So I'm going to give two pseudocodes, and I will spend the remaining minutes on that. And that basically tells you how you do this, and if you look at the MATLAB code, it's surprisingly similar. Okay, so what are we going to do? We're going to compute the objective, that's F, so that's the misfit, so the energy, the misfit between observed and the synthetic data, and G, that is the gradient. Those are the two components that solvers like LFVGS need. Okay? And then I'm going to do a loop over the index of shots that I selected. So I have a random subset of shots. I'm going to loop over that. I'm going to solve the forward wave equation up to epsilon. So I'm going to tell my Kratzmark solver, iterate until the epsilon is done. Okay? And I set this epsilon to some value. Then I compute my residual. Then, if my residual between the current iterate and the previous iterate is some fraction of the residual, then I'm done. Else, I tune in my epsilon. I go finite. Okay? So now, if I'm done with that, I have an epsilon now I can solve my adjoint system up to epsilon or less. Because adjoint systems are typically an order of magnitude, an order less accurate because they depend on the data decision. So you can do things less accurate if you wanted to. Then you compute your objective, and because you loop over the shots and your gradients, you accumulate them. So this is an algorithm that works in parallel. Okay, so let's have, now you have your objective and your gradient. So now you can give it to a black box solver like LGS, but you need to do something for that. And so you need now a couple of additional ingredients to make this work, because now it's a second order method, so it uses basic information on the Hessian that's formed out of previous gradients, so this becomes now a bit optimization lingo. So what we need to do the following, so we're going to do now for each, after each model update, we're going to draw a new set of sources and compute the misfit and the gradient in the way that I just described. Then we're going to, if the line search fails, we're going to dial in the tolerance that we introduced to compute these accuracies. We use wolf line searches. We increase the sample size when the average objective does not increase. So we have an objective and a second one. And I will tell you in a minute why we have two. But the average of these two should be basically smaller than this one. If not, then we have to dial in, we have to increase the sample size. Okay. So maybe it's the best thing to just show you the algorithm. I promised some algorithms that you can code up. I will leave the slide. So this sort of puts the whole thing together. So we select a random subset of shots. We do the misfit calculation that gives us the objective and the gradient. As long as we not converge, we do a model update using LPGS that uses previous gradients and these T and Ys, which is basically information it needs to build up a low-rank inversion of the Hessian. Then we do a line search. If the line search is successful, then we compute a new misfit from a new realization, a new random selection, I should say, of the sources. Then if we make progress in the objective, we increase the counter by one. If not, we have to increase the size of the number of shots we use. And if the line search is not successful, we have to dial in the following. So you have to stare at this for like half an hour. It makes sense. So this is a way, and I'm going to stop now with all the detail, to basically dial in accuracy as well as the number of shots that you need in your inversion. So it gets technical, but that's what you need. So I think I can stop here, or I can show an example. Where are we?
Is the example pretty?
Is the example pretty? Yeah,
you show an example. Yeah,
it's pretty. It basically shows that this does what it needs to do. Let me go just to the main example. So this is an overtrust model. So we have a three-dimensional model here, and so this is the true model seen in the XZ, XY, and YZ. We have about 2,600 receivers, about only 121 sources. So this is a small problem, but mind you, this can scale to much larger problems. This is the initial model, so a very smooth version of the true model. And then we did two experiments, so we'll only show experiment 2. Okay. So we do several passes through the data while we increase the frequency. So that's typically what people do when you do Fourier inversion. You start at low frequency, then you go to higher frequency, and we do basically 3 passes through the data. And here you see the misfit, and here you see the number of passes through the data. In black, it means we work with 1 shot. In dash black, we work with all the shots. And in red, it's when we work with a dynamically selected number of shots. Okay, so you can see that the misfit goes down with iteration, kicks up if you go to higher frequencies, kicks up, but in general, it goes down. The behavior is much smoother for the when you increase things, but less smooth than if you use all the shots to compute your data. This is the model error. You can see that the model error, when you use all the data, doesn't decay very fast, whereas the model error for the single shot case, it goes down quickly, but if you increase the number of shots, it will gain when you go to try to fill in more details of the model at higher frequency. This is the accuracy. That's how accurate do you need to solve CVEs. If you can see that the accuracy, you will have to be more accurate as your model becomes basically as you bring the model error down. So you see a trend downwards when you dial in the accuracy. And this is the number of iterations that you need. So the number of iterations of the solver basically increases slowly, as you would expect, because the accuracy needs to be higher to make sure that you converge. And this is the sample size. So when you work with one, you have only one. When you work with 121, you have to work with all 121. And with our method, we slowly dial in the number of shots in order to reduce the error that you created by subsampling the shots. That's it.
Thank you.